All right. So today we have Justin Hilburn, who will tell us about two categorical 3D mirror symmetry and symplectic duality. Take it away.
Okay, so yeah, and I just want to say that like a lot of this stuff is pretty new and like pretty unfamiliar. So I kind of encourage people to just bug me whenever I say something that sounds weird or sounds or that you'd like to hear more about. I'm basically just trying to like advertise this program as much as I can, and yeah. Anyway, and so just anything that I can get people to understand about it would be good. So this is joint work with Ben Gamage and then also Aaron Mazelji, although wasn't involved in the most recent paper. And then I'd also really like to thank Matt Bullimore, Tudor Demafte, and Davide Gaiotto for basically back when I was writing like my very first physicsy paper. They taught me, in return for me teaching them about symplectic duality, they taught me everything I know about 3D n equals 4 theories. And like none of this really would have been possible without them. So I really would just like to thank them for that. All right, so the thing that I'm trying to do is sort of should be patterned after like what people did about 2D mirror symmetry like back in the 90s, where we learned thanks to Witten and Kontsevich, that 2D mirror symmetry is some sort of relationship between two-dimensional n equals 2, 2 supersymmetric quantum field theories, that there's some duality like on this space that has the property that it exchanges the two topological twists. So these 2D n equals 2, 2 theories have two topological twists. One of them is called the 2DA model, and the other one is called the 2DB model. And the way that these things like work in a particular example, say like the Calabi-Yau sigma model, which has like some field which I'll call sigma, which is some map from a Riemann surface into a fixed Calabi-Yau. And the way that these two topological twists work is that this A model is basically built by studying the de Rham cohomology of the space of holomorphic maps. So like this field sigma, like in the actual quantum field theory, like it obeys some like more complicated equation, but like after you twist, like it just obeys the equation that it's like holomorphic. And the fermions in the theory basically end up telling you that you're studying de Rham cohomology. Then there's also this second topological twist, which is called the 2DB model. And in that one, your field ends up becoming like a locally constant map. Basically, for this reason, people or mathematicians often forget that there's even a map in the B model. And then the fermions end up telling you that you're going to end up studying like Dolbeau cohomology of this moduli space. And like the thing that you'd like to do is you'd like to find some mathematical object that summarizes like all of the data in these topological quantum field theories. And what Kontsevich figured out is that like these topological quantum field theories are just completely determined by their categories of boundary conditions. And so the first one for the A model is the Fukaya category. And so there, right, you study like Lagrangians, and then you study, holomorphic maps whose from Riemann surfaces with boundary, like on these Lagrangians, and then also like in the B model, you have the category of coherent sheaves, and that's like basically built through like Dolbeau cohomology of like coherent sheaves. And then what Kontsevich realized is that these categories encompass like basically everything about these quantum field or these twisted quantum field theories. And you can summarize 2D mirror symmetry as just being some equivalence of categories between the Fukaya category of a Calabi-Yau and the coherent sheaves on its mirror. So this is like an old story that people like know pretty well. And like I would like to do this, I'm sorry, and actually let me just say something about like a very simple example of this, because it'll have some features that I want to say later. So like the simplest example of this is like you don't necessarily have to study Calabi-Yaos. You can study more general symplectic manifold, something like T star S1. And the mirror to that will be a complex manifold, say C star. And like the simplest example of this mirror symmetry is that the hyper-Kähler category in this case, which when you have a non-compact manifold, there's like a lot of different hyper-Kähler categories that you can associate to a given non-compact symplectic manifold. And they're determined by some piece of data, which is called like a Lagrangian skeleton. And so in this case, my skeleton is just the zero section. And this hyper-Kähler category in this case can be modeled by like the wrapped microlocal sheaves on T star S1, or just the local systems on the base, on the skeleton. And those things are just vector spaces with an action of the fundamental group, which in this case is Z. And since it's linear, like you can linearize the fundamental group to just get the space of chains on Z. And that is exactly going to be functions on C star. And that generates the category of perfect complexes on C star, which maybe later I'll want to think of in some micro-local way in terms of shifted symplectic geometry, but I'll leave this off for now. But the only thing that I wanted to like say just by doing this example is that under this isomorphism, the generator on the hyper-Kähler category side is the cotangent fiber to 1 inside of S1. And the important thing about it is that it's transverse to this skeleton. And when you compute the HOMs, there's a particular phenomena that you need to like take into account, where because this thing is compact, when you compute the endomorphisms of this cotangent fiber, when you displace it, you need to wrap it around the cylinder a bunch of times. And then you'll get this integer's worth of intersections, which are exactly in bijection with like the fundamental group of S1. And that's like what's responsible for this Z here is this wrapping behavior. And like the thing that's going to come up for us a lot in this 3D mirror symmetry stuff is going to be dealing with this wrapping. So maybe I'll just stop. Is there any questions about this phenomena? Okay. All right. So I kind of want to do the same kind of thing, but for a 3D n equals 4 quantum field theory. And so there, the canonical example is the hyper-Kähler sigma model. And so that has a field which is now no longer a map from a 2-manifold into a Calabi-Yau. Now it's a map from a 3-manifold into a hyper-Kähler, into a fixed hyper-Kähler target. And then there's some fermions in the theory, which I'm not going to write down. And then these 3D n equals 4 theories, they have like 2 families of topological twists. The first kind, or the most studied kind, is the 3D B model, or Rozansky-Witten theory. And roughly, like this thing looks very much like a 2D B model. In this case, again, your field becomes locally constant. And you're going to study Dolbeault cohomology of this space of maps, or like of various spaces of maps related to this. And there's a second twist, which is maybe slightly less familiar, which is the 3D A model. And this one also looks very much like what's going on in 2D. So here, your field is going to satisfy the Dirac equation. Your field sigma here is going to become a spinor, and or a y-valued spinor, and you're going to study solutions to the Dirac equation and study de Rham cohomology of that moduli space. And here, like if you trivialize your if your three manifold is just R3 and you trivialize everything, then this equation just becomes what's known as the Footer equation, which is that your map needs to satisfy like I ddx plus j ddy plus k ddz times sigma is equal to 0. So that's what this Footer equation is. And basically, we're going to study, if you were to study this thing analytically, you would end up studying like the de Rham cohomology of these moduli spaces. And again, like I'd like to know, well, sorry, and again, there's like a mirror symmetry operation that acts on the space of 3D n equals 4 quantum field theories, and it exchanges like the A twist and the B twist. And I would like to find some way of like phrasing this in like a mathematical manner. And so the way that I'd like to do this is you'd like to formulate some sort of a two-categorical 3D mirror symmetry program. So basically, it's well known that basically three-dimensional topological quantum field theories are described by two categories. The reason being is that you have, your boundary conditions being your objects, then you have like your boundary lines. Let me maybe just draw this. So, you have like your three-dimensional space, and then your boundary conditions are basically the objects of your two category. Then you have like your boundary lines. These things are like the one morphisms. Like if I have two different boundary conditions. And then if you have two different boundary lines, you can put on like a boundary local operator, and that thing is like a two morphism. So we should expect that the algebraic structure that we're going to see here is some sort of like a two category. And so the two categorical 3D mirror symmetry program is going to be build a two category out of the Footer equation and build a two category out of the Rozansky-Witten theory associated to a hyper-Kähler manifold. And then if you have two 3D mirror hyper-Kähler manifolds, then the A-type category, the one built from the Footer equation, is going to be will be equal to the B-type two category, the one built from the Rozansky-Witten theory of the mirror. And I just want to say that actually this is kind of way too optimistic to be the correct answer. The first thing that goes wrong is that it's very rare that a hyper-Kähler sigma model is 3D mirror to another hyper-Kähler sigma model. So this class usually isn't closed. So you will almost always have to consider gauge theories in order to get closure under 3D mirror symmetry.
You refer to a hyper-Kähler manifold which is smooth and compact?
Not compact. Basically, the compact ones are interesting, but I'm never interested in that class myself. I'm always going to be interested in something I'll say more specifically in which case in which cases that I can actually make this work. But the cases that I'm going to be interested in are mostly when things are hyper-Kähler reduction of a vector space. So that's when you've got a gauge theory.
Yeah, and I see. So then you could talk about the symplectic singularity, possibly?
Yeah, so that's the main class that I'm going to be interested in, is symplectic singularities. But it is actually interesting to study these two categories. It is interesting to study these two categories even when things are compact. I just don't know any mirror pairs. That's my ignorance. I don't know, for example, I don't know what is the 3D mirror of a K3 surface, for example. That's a question that I don't know the answer to. And so the class where like I know how things work is basically these symplectic singularities.
But you could also ask what happens in cases that there is no hyper-Kähler quotient or Hamiltonian reduction. For example, take minimally 6. It's a nice symplectic singularity.
Absolutely. And I'm basically not able to do those right now. So that is a class that should work, but it's just like it's beyond like our ability. So I'll tell you which ones we can do right now, and it's like basically I can do a billion examples right now. A billion gauge theories are all I'm going to be able to.
You'll use Gale duality, I guess.
Just use Gale duality, but that's not the class that I think it will eventually be. Eventually, I believe it'll be these at least the symplectic singularities, if not more.
Okay.
But right now, like that's the only example we can handle.
Okay.
Can you say a little bit more about these boundary conditions that, what type of boundary conditions?
Yeah. I'll say that in a minute.
Boundary conditions or.
That's going to be the rest of the talk.
Oh, okay, great, thanks.
I'm just setting up the fact that there's going to be like a 2-category like in the game. Its objects will be boundary conditions. Just like normal, its objects will be the boundary conditions, the morphisms will be the boundary lines, and then the boundary local operators will be the 2 morphisms. But that's just for any 3D TQFT. That's not special to this at all. Okay, so that's like the first thing that's going to go wrong, is that this fact that I don't know like closure, like for like the hyper-Kähler sigma model, so we'll have to have some gauge theories. The other thing that's going to go wrong is that the examples that I'm going to study are going to be usually not compact. And when they're not compact, you need to do something to like regularize, to regularize your theory to get some like reasonable answers. And this is very similar to in this 2D example, when I was saying that like there's not just one Fukaya category associated to T star S1 to the cylinder. Like basically there are lots of Fukaya categories involved, and they're determined by this data of a Lagrangian skeleton. So like I did this example where my Lagrangian skeleton was the 0 section, and then that was the thing that gave me my mirror being C star. But a different example that I could have done is if you take the cylinder and then you give it this Lagrangian skeleton, where you take the 0 section and then say I take this real Lagrangian being like a cotangent fiber going off to like to one side. Like this example like ends up being mirror to just C instead of C star. And the reason that this is true is that the way that this stuff works is that these things are the skeleton basically tells you, it determines some point for you in the boundary at infinity, and that thing stops the wrapping. So what's going on, like in this example, is if you take like your cotangent fiber and then you try and do its intersections with itself, is you can wrap in this direction, but you can't wrap here because you would cross the skeleton at infinity. So that's like what's giving you like only half of like only the like maybe the negative elements of your fundamental group, and that's like what's responsible to the fact that you're seeing just functions on C instead of functions on C star in this example. So this is something that's very familiar, like in the Fukaya category, and something like this is going to come up here as well. That like the most subtle part of this is that like you're going to have to do something to control the behavior at infinity, and in the physics that's going to be coming from the mass parameters, or it's going to be coming from like what's called a Lagrangian skeleton. So anyway, like basically the rest of the talk is just making sense of like what this slide says. But these are kind of the issues that we're going to see. All right, so let me just say like physically, like what do we actually know about computing these 2 categories? So let me assume, so like once you've chosen A and B twists of the same theory, and you've chosen a splitting of R3 into R times R2, then that chooses for you basically like a 2D 2,2 subalgebra. And the nice thing about this this subalgebra is that we can rewrite our 3D n = 4 theory. We're going to rewrite our 3D n = 4 theory as a 2D theory into a path space, and in order to compute like what the boundary conditions are, and the A and B twists of this 2D theory are going to match the A and B twists of the 3D theory. So what we can end up seeing is that like once we've chosen this subalgebra, then that chooses a complex structure on our hyper-Kähler manifold, making it into like an algebraic symplectic manifold. And I want to just go ahead and assume that it's going to be exact for simplicity. And the way that you can figure out like what are the boundary conditions, or you can rewrite this 3D theory like as this 2D theory into a path space. So the space of paths that we're going to be looking at is initially maps from the interval into our holomorphic symplectic manifold. And in order to make this 2D theory recover the equations of motion for a 3D theory, you need to introduce a superpotential. And the superpotential is going to have the following form when you evaluate it on a path. Then you're going to just take the integral of the pullback of this Louisville one form, this one form here, such that d of it is your symplectic form. And then there will end up being like some boundary terms, but let me just focus on this bit of it for right now. So basically, this is just a holomorphic version of like the ordinary symplectic action functional that comes up like when you study like a 2D theory. So this thing is just like the integral of P dq, but now P and Q are complex. If you write this down in coordinates, this is just like the integral of like P dq over 0 to 1, except for when you're doing ordinary floor theory, this is a real function. But now that since this thing is holomorphic, these are like holomorphic coordinates. So this is a complex valued function. And then if you just do the ordinary analysis that you would have done in floor theory, just like when you were setting up the Fukaya category, you'll see that in order to like cancel the boundary terms that show up when you try and compute the variation of this functional, like you need to actually have certain boundary conditions at 0 and 1. And it's like a very easy exercise to show that like they actually need to end up being exact holomorphic Lagrangians. So what you find is that in order to make this this LG model from this on this path space well defined, you find that you need to make impose holomorphic Lagrangian boundary conditions. And that analysis basically tells you that the objects of these two categories are going to be exact holomorphic Lagrangians. Does that make sense? I don't want to go on unless this makes sense.
I think it makes sense.
Okay.
But it could be also, I mean, if you provide examples, it will be nice.
An example. Yeah, okay. Let me see what I can do. Yeah, so all I'm saying is that like suppose that you're studying so we're studying like maps from R3 into some particular holomorphic symplectic variety, let's say T star C. So here the symplectic form is dp wedge dq. where P and Q are the coordinates on T star C. Like Q is the base coordinate and P is the fiber coordinate. These are holomorphic coordinates.
Would be
yeah.
T star of C. Okay, yeah.
Yeah, so this thing has coordinates Q and this one has coordinates P. So this thing is, so this is my holomorphic symplectic form. And I have my Louisville form. And now I want to go ahead and rewrite this thing as maps from R2 into, maybe let me say that this thing was a 0, 1. Times R2. So now I want to rewrite this thing as maps from the interval into T star C. And now, you know, in order to recover my 3D n equals 4 equations of motion, I'm going to want to not just study, you know, a 2D theory just into this mapping space. I'm going to want to like impose a superpotential. And I'm just telling you that the one that I'm going to end up needing is the one that comes like this. So sorry, this is the value on a given path. So this thing, so I want to define some function here such that on a given path, I pull back this Louisville 1 form and then integrate it. But that thing ends up being just, you know, PDQ.
So if the superpotential varies, then typically from the physics perspective, supersymmetry is broken.
Sorry, it's not, the superpotential isn't varying. What? Sorry. I'm just saying, rewrite my 3D theory as a 2D theory and with an infinite number of fields. And basically you need some sort of a superpotential to deal with the cross derivatives, like the derivatives. So the 2D equations will handle all the derivatives that just involve this R2. And then I need something that handles the derivative, like the cross derivatives in this 0, 1 direction and this R2 direction. And the way you put those in is by putting in a superpotential. Like into this 2D theory. And then all I was saying is that now, like, this thing is ill-defined, because if you try and compute the variation of the superpotential W, you'll end up computing the integral of the variation of P dq plus P times the variation, you can pull the variation through, times the variation of Q. And you would like to eliminate this term using integration by parts, like in the ordinary way. And so what you find and then you find, sorry, that should have been with a minus. And then you pick up a term that looks like the variation of Q times P. So this evaluated at the boundary of your path. And what I'm saying is that in order to make, so this is the equation that I would like to get. So this thing here is basically evaluating your symplectic form on the t derivative of gamma and the variation gamma. And this is the term that you would like to have coming from your superpotential. And in order to get that, you need to impose some boundary conditions. And you find here that the simplest thing that you could do is you could just ask for P to be 0. And that's telling me that at the boundary on 0 and 1. And so what that's telling you is that this thing needs to lie on the 0 section. And so that's like a holomorphic Lagrangian boundary condition. So in order to cancel out this variation, like you end up like asking that you have exact holomorphic Lagrangian boundary conditions. And if you added some like boundary terms to the superpotential, you could get like any exact holomorphic Lagrangian that you want. Like I could make this thing land on any graph of any DW. So I don't know if that was actually helpful. It seems like it was not. So what I'm saying is that in order to figure out what the boundary conditions are going to be that I'm going to be interested in, is you rewrite your 3D n equals 4 theory like as a 2D 2,2 theory, like into this path space with the superpotential, and then you basically do the exact same analysis that I just did. And it tells you that in order for this thing to make sense, you need that the endpoints of your path get sent to exact holomorphic Lagrangians. And then now if you want to know, so I wanted to get a 2 category out of this, either for the A twist or the B twist. And the way that you find that 2 category is you just take this 2D LG model and you just and you do the 2D A or B twist. So the objects in either of this A type 2 category or the B type 2 category are going to be exact holomorphic Lagrangians, and the morphisms between them are going to be given by either the Fukaya-Seidel category of this mapping space with potential, or the matrix factorizations of this mapping space with superpotential, depending on whether you want the A twist or the B twist. And then in a special case, if you knew that your Y was actually a cotangent bundle, and these Lagrangians were actually the graphs of graphs of the derivatives of holomorphic functions, then like this thing reduces either to a Fukaya-Seidel category on the base with your function f1 minus f0, or matrix factorizations on the base with f1 minus f0. So maybe like so this isn't actually what I'm going to do, but this is like what the physical analysis would tell you. Does this make sense? I feel like I
guess it's a little difficult to connect to the way that the 3D mirror symmetry is viewed as like by a physicist of, you compute a Coulomb branch, a Higgs branch of something, and then you have a different theory where you can compute these things and they're switched.
Yeah, so that's right. So basically I have not tried to do, so right now, like we basically only kind of, with a sigma model, you basically only kind of have a Higgs branch.
Yeah.
And I've not done any mirror symmetry whatsoever yet. All I've done, I've just said, like, if I have like a sigma model, I can build 2 categories.
Yeah.
Like I've not said anything about mirror symmetry at this point.
Sure. Yeah.
So this
there's also another point that if we take T star of C,
yes,
so, I could just use a free hyper.
Yes, that's what this one is, a free hyper.
Free hyper. Then in physics, we will put no superpotential because it's free.
That's right. But when you rewrite it as a 2D theory, the 2D theory has a superpotential.
Will still have no interactions. It's free.
No, you need like something. You need something in order to get the. It's just like if you were to study like T star R in 2 dimensions, and then you like write it as like a 2-dimensional, like as like a 1-dimensional quantum mechanics, you pick up a superpotential.
Not if it's free. so that's where the difficulty comes. So I'm not.
You need it in order to get the, like, for the one-dimensional equation on the path space, like to pick up the cross derivative. Like basically, like if I just wrote this thing with no potential, then your theory would only have derivatives like in the R2 direction. Like if I, if I take my R3 and write it as R2 times 0, 1, like if you just write down a 2D theory into this path space, there would be no like cross derivatives that like mix the two directions and the third direction. And that's all this potential is doing, is it's just like mixing the three. It's just like what's giving you the cross, the third derivative.
I suppose that the necessary step is to do the twisting.
Yeah, yeah, it's just to get this Futter equation, which like here has, it involves all three directions, like in the derivative.
So we will need some work here to do the translation. It's not so clear.
Okay, yeah, so I apologize. I maybe didn't spend as much.
But, yeah, I mean, it's okay. It's not...
No, I know, but basically I just want to be understood, right? And so like, and it's my fault if I'm not. So let me like try and
it's all good.
Yeah, so let me maybe
move
try
forward, and I'm sure we can connect.
Yeah, so let me now try to say a little bit more about what I'm saying that the HOMs in the A model are. So I said to compute the HOMs. So again, in either the A model and the B model, my objects are going to be these exact holomorphic Lagrangians. Now, if I have, and my favorite example would be like if my variety is just T star of something, and these things are just the graphs of, holomorphic one forms. Particular D of a function is my favorite one form. And like now I would like to compute the HOM between two of these things. And so I say that like, okay, you should look at this path space. And now you should do its A twist, and that thing will give you some Fukaya-Seidel category. But you should immediately start screaming at me, because like this thing is infinite dimensional. Right, maybe a physicist wouldn't scream at me, but a mathematician would scream at me. Yeah, and say like, this thing is infinite dimensional, what are you doing? Mm-hmm. And so I just want to mention that there's like a particular model for the Fukaya-Seidel category that deals with this infinite dimensionality. And it's called the algebra of the infrared. And basically, like here, the way that it works is that the objects of this Fukaya-Seidel category, we're not going to study thimbles like coming from the critical points, which is like what people normally do. We're just going to study the critical points themselves. And if you look at the critical points of this function that I just told you, its critical points are actually just the intersection points of L0 and L1. Let me assume that they're transverse. So then so they intersect in a finite number of points. So then the critical points would just be like the intersections of this L0 and L1. So like if you take, and that's just exactly like the computation that you would have done for the 2DA model. It works exactly the same way. It's just that it's complex now instead of real. And then now if you want to compute, and then and just like, in the ordinary floor theory, you take a complex, which is like generated by all of the critical points. Now I'm going to make a category, and it's going to be generated by like direct sums of all these critical points, and maybe twisted complexes of these critical points. And those critical points, again, are exactly these intersection points. And then now, if you want to compute the morphisms, so now if I want to take two of these critical points, those are the objects of this Fukaya-Seidel category, and now I want to compute the morphisms between them. Well, this model, this algebra of the infrared, tells you that's going to be generated by the gradient flows. Normally, if you have like a complex function and you have two critical points, there's no gradient flows in between. But like you can actually like find, if you take the real part of the function and look at gradient flows, you won't find any gradient flows between two critical points. But there are these exceptional angles where, like, if you look at the argument of the value of my superpotential on P and on Q and take the difference, so that's some complex number, and then take the argument of that complex number, that's an angle. And now if you take e to the I theta times that angle, or sorry, times the superpotential, and then take the real part, you actually will find some gradient flows. So that's a surprise that's going to happen. And if you rewrite these things, like if you reinterpret these things in terms for this particular action functional, you find that they're actually J theta holomorphic strips connecting these two critical points with boundaries along the Lagrangian.
Yeah, actually,
where J theta is going to be just let me say, it's the cosine of theta times J plus sine of theta times K, where those are the perpendicular complex structures.
Mm-hmm. I see.
Yeah.
How easy is it to describe what happens for T star of Pn?
Yeah, so for T star Pn, it's pretty hard, and I can't do it in these terms yet. So that's like basically like the thing that I'm working on right now. I'm going to tell you that I have a different way of computing these things, which is not like directly in terms of counting solutions to a PDE. There's like a different way that one can try and do this.
And one more question is, you said before symplectic singularities, but you seem to prefer resolutions of symplectic singularities?
Sorry, yeah. So basically, the mass term on one side, which is going to deal with the non-compactness, is going to resolve the other side. As you know.
And you want it to be present.
Yeah, I don't know what to do when it's not present.
I see. Mm-hmm, mm-hmm.
Okay. So anyway, so we've still not said anything about mirror symmetry, right? All I've done is just like tried to tell you like what is this two category possibly going to look a little bit like on the A side. And then on the B side, this two category is actually very well known. This was constructed by Kapustin, Rozansky, and Saulina. Basically, they gave this model that when it's a cotangent bundle and you have just graphs of graphs of df, where f is a function, you just take matrix factorization of the difference of the functions.
Mm-hmm. And if it's a resolution of a Klein singularity, let's say of type A, is this easier to?
They're all of these are about at the same level of difficulty. The T star Pn is in particular an example. But let me. Yeah, so I was going to do something, but like, let me change path, maybe just to get you, basically, I feel like you won't like this. So let me do something different. So let's like do the actual examples that I am interested in. So I'm interested in these abelian gauge theories, where you have, or like a hypertoric variety. So these things come from, like an exact sequence of tori, where I have C star to the n acting on T star C to the n. I choose like some subtorus, and I have my flavor torus as the quotient. And then I'm going to be interested in the scenario where I'm going to have no complex, because I've chosen this 2-2 subalgebra, like to look at the boundary conditions, I have a splitting of my mass and Fi parameters into real and complex parts. And so I'm gonna just set the complex parts to be 0 for now, and I'm just gonna look at the like the real Fi parameters and the real mass parameters. And as you've said, the real Fi parameters, they contribute to like a GIT quotient, which is like a resolution of what you would get if you set T to be 0. And I'm going to choose like a real mass parameter. And this real mass parameter determines like a Lagrangian inside, which is like an attracting set. And the mirror symmetry swaps the roles of F and G, like you take Langland's duality of the whole sequence, swaps the roles of F and G, and it swaps the roles of M and T. And so let me just do like a little tiny bit of geometry on these guys. So I want to try and describe this attracting set in some sort of combinatorial fashion. So for each sign vector, like a plus minus to the n, I can describe a particular subset for you of this quotient stack, or like this is, and it's just you set the x's equal to 0 whenever the whenever you have a whenever you have a minus, and you set the y's to 0 whenever you have a plus. So so like plus plus would set both of the y's to be 0. Sorry, if I had like T star C2 and I said like what's the Lagrangian corresponding to plus plus, well, that would set both of the y's to 0, so that would be the 0 section. If I asked you what was minus minus, that would be the cotangent fiber to 0, because I would have set both of the x's to 0. So this is just some way of parameterizing a bunch of like nice Lagrangians inside of my inside of T star C to the n. And then I can reduce them to get into this hypertoric variety.
So the x's and y's, sorry, that their x are, what are these coordinates?
Oh, I'm sorry. These are, I guess I was calling them P and Q before, so let me.
Okay, so the P, yeah, fine. It's okay. X and y is also fine.
Yeah, whatever. QI. All right. And there are two like nice, so I want to describe two very nice sets of these sign vectors. So this is just some combinatorics. So I want to describe the feasible set f of t. This is going to be all of the alphas such that when you intersect with the t stable locus, you actually get a non-zero intersection. So these are all the L alphas that are going to survive into the GIT quotient where you impose the t stable condition. And then also the bounded chambers for the mass parameters. These are going to be all of the ones that are contained inside of this Lagrangian. And the claim that I want to make is that if you intersect the Lagrangian lambda, which is the union of all of these L alphas, with the semi-stable locus, well, by definition, that's just these feasible guys. And by definition, lambda m is just the union of all these bounded guys by definition. So I haven't said anything interesting yet. I've just restated the definitions. But the interesting thing that I wanted to say is that these two sets are actually swapped under the 3D mirror symmetry. So basically the bounded chambers and the alphas that determine bounded chambers in one theory determine the feasible chambers in the mirror and vice versa. So let's do this like in an example. So the example that I'd like to study is say T star P1. So in this case, you have C3 with like the diagonal C star. That quotient is T star P2. And here you have three bounded feasible chambers, which would be the 0 section, the cotangent fiber to a P1 inside of my P2, sorry, the conormal to the P1 inside the P2, and then the cotangent fiber to a point inside of my P2.
Wait,
And then on the other side, sorry?
T star of P1 or T star of P2?
P2, because I have 3 hypers.
Yes, okay. Mm-hmm.
So it's a P2, and this is the toric picture of P2, right?
Right. Yes.
And so if you draw, so there's like a hyperplane arrangement that one can draw, encompassing, that's like a generalization of the toric combinatorics, which tells you how these Lagrangians, special Lagrangians that I was describing, sit inside of your hypertoric variety. And basically the sign vectors are basically determining for you like what side of each hyperplane that you're on. So like plus 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 is like on this front of this hyperplane, and this hyperplane. And so this one, for example, is the 0 section, right? Because I'm setting all of the p's equal to 0. And that is exactly a P2 as you would expect. And then your mass parameter is determining for you a functional on this hyperplane arrangement. And the way that you tell whether a chamber is in the attracting set for the mass parameter is you ask, does this function attain a maximum on this chamber? And you'll see that like for three of these chambers, it's bounded, but on each of, like, say, this chamber, this function m like never attains a maximum. So that tells you that this attracting Lagrangian is the sum of these 3 chambers, or the toric varieties corresponding to these 3 chambers, which is a P2, this conormal, and this T star P2. And if I do this on the other side, like on the Gale dual side, you find a similar hyperplane arrangement, now just with a line with 3 different hyperplanes on it. And then you notice like which guys are actually bounded for this mass parameter and you find these 3 chambers, and you notice that the sign vectors are like exactly the same. It's plus plus plus, plus plus minus, sorry, plus plus minus, and plus minus minus. So the thing that this is meant to illustrate is that the feasible sets being the stable components and the bounded components, the ones that are in this attracting set for your mass parameter, are swapped under the 3D mirror symmetry. Okay.
Another question is how is this discussion affected by having symplectic leaves in the singularity? Is this
it's not. This is not particularly affected by the leaves, because I can get multiple leaves in a hypertoric variety, and all I've done. So I haven't done anything particularly interesting. All I've done is just given you a combinatorics. So I had defined, this open hypertoric variety being the GIT quotient with respect to this real Fi parameter, and defined this real mass parameter, which is something in the flavor, and defined its attracting set. And I've just given you some combinatorics for talking about these guys, like for describing the attracting set and the feasible set. So these 3 chambers here are in both. And I've just noticed for you that when you have Gale dual hypertoric varieties, that the feasible bounded set, the ones that like are in the GIT quotient and in the attracting set, are matched under the mirror symmetry. And the formulation of the 2 categorical abelian 3D mirror symmetry that I want to take is that the 2 category associated to my 1 hypertoric variety with a skeleton determined by this attracting set is going to be mirror to the B type 2 category for the Gale dual hypertoric variety with the Gale dual attracting set. So that's going to be the formulation. So this is...
I'm a bit confused. Is it that the A3D on the left is isomorphic to the B3D on the right, or mirror? Like I thought that A3D and B3D of one thing would be mirror. And then A...
So these are A3D and B3D of mirror things, right? So if I have two mirror theories, then the A twist of one ought to be isomorphic to the B twist.
Okay. So that's an okay. Good. So this is an isomorphism between A and B.
Yeah, that's right. So it's the same. It's the same as like the ordinary two categorical.
Okay, good.
Mirror symmetry, and now the and so now like the whole game becomes. So I said that this is a theorem, but the way that like because I've skipped some stuff, the I haven't told you what these two categories are precisely. So this one actually like is defined precisely like like with what I told you about with Kapustin, Rozansky, and Saulina. And this one is almost defined, could almost be defined if we were better at counting Futter maps, but we are not. Okay, so let me just say a couple of other things before I move on. And this is the question of what are the generators of A3D? All right, so let me like look at this example that I had written down, where I've basically got this guy and this guy. And maybe if you want to draw it, looks a little bit like this. Sorry, I have an extra hyperplane. Where this is a P1, and a C. These are just the toric pictures of that. All right, so this is something that I learned from something of Telemann. And so the generators that we're going to find in this case is that this B side, this guy is going to be generated by the components of the skeleton. So that means that it's going to be generated by like three objects, being this P1, and this cotangent fiber. And this one is going to be generated not by the components of the skeleton. This thing is actually going to end up being generated by things that are transverse. So the picture that you have in mind is, let me maybe draw like a slightly different example. So like if I had this guy on the A side. The Lagrangians that I would be claiming that I actually want to look at are not the core components, but they're things that kind of look like this. So they touch each core component. So there's going to be 3 generators again, but they're going to be like Lagrangians that like are transverse to the core components. And so let me tell you why I know that this is like the way that things are supposed to work. Okay, so now I'll go back to the thing that I said that you weren't going to like, but I think that now we're ready to hear it. So I want to talk about the only example before I had done any work that had been worked out. The only example of 2 categorical 3D mirror symmetry that had been worked out before like I got involved with the subject. And that was basically worked out in Telemann's ICM address. And so this is like the prototype for like everything that we want to do. And the amazing thing about the way that he did it is he managed to give a definition for the A model that didn't involve counting any, solving any PDEs. And so he worked out the simplest example. So let G be just some torus, some C star to the n or some U1 to the n, depending on whether you like complex or compact groups. And the simplest mirror pair is going to be the sigma model into the cotangent bundle of the Langlands dual group, which again is just going to be a different. It's also going to be a C star to the n, but it's going to be the dual one. And the mirror is going to be pure G gauge theory, or for the compact form, if you're a physicist. And so I like to think of that as just being something about the holomorphic symplectic manifold T star BG. Like basically, whenever physicists talk about gauge theories, like I just like to talk about stacks. And he worked out and he basically gave the following putative examples for what the A type 2 categories and B type 2 categories for these things should be. So he said the following. So let's just think for a second about what I would have said that the A model, just the ordinary 2D A model of T star G Langlands dual would have been. So whenever you have a cotangent bundle, roughly the Fukaya category should just be something like local systems on the base. And Telemann said, like, why don't I just not look at local systems on the base? Why don't I look at if I want to study the 3D A model, I want to get a 2 category. So I won't look at local systems of vector spaces. I'll look at local systems of categories. And that was his like putative example for what the 3D A model should be. So he didn't count any footer maps and he didn't like do anything. He just was like, this is what I think that the answer should be. This is my ansatz. And if you, and in a second, we'll see that this thing is actually like a pretty good ansatz because it'll satisfy 3D mirror symmetry. But let me like just very quickly like do this again on the other side. So on the other side, you could also look at the 3D A model now of T star BG, and he would tell you the same thing. Well, this is a cotangent bundle, so I should look at local systems of categories on BG, and that will be the answer. Okay, so that's like all pretty good. So that's like what these A sides are. And then if you want to like actually like make these things like a little bit like more concrete, a local system of categories should just be defined to be a functor from in 2cat from this topological space viewed as a category into the 2 category of C linear categories. And since this is a K pi 1 space, you can, it's really just the classifying space of its fundamental group. So you can think of this as actually as being a functor from the category with a single object, and then one endomorphism, one automorphism for each element of the fundamental group into the two category of categories. And so when you unpack all of this, you find that such a functor is just the same thing as the data of a category plus one automorphism for every element of the fundamental group. So this is like, and this is the same as when you would say a local system is just a vector space plus an automorphism for every local system of the fundamental group. And so that isn't like too bad. And you can do the same thing on this side. And now you will again use the fact, so you'll say that, okay, it's just a functor from BG viewed as a topological space into from this topological space viewed as a category into the two category of categories. This thing is again a k-pi1, so it's really just a map from the second classifying space of the fundamental group into the two category of categories. But now things are shifted. Such a functor is now just a category, but now with a map from the fundamental group into the endomorphisms of the identity functor. Does this make any sense at all?
I have to say, personally, I'm not following this E2.
Yeah. So like what this category, so right, if you think of your topological space as a category, this is one, looks like one where you have like one object, which has a single endomorphism. And then for every element of the fundamental group of G, you have a two-morphism. So you have one two-morphism gamma for every gamma in pi1 of C. So this is what the thing B squared pi1 of G looks like. And basically it's because, right, like BG, it's connected. So it's basically up to homotopy, it's got 1 point. And then it's also going to be simply connected. So like up to homotopy, it's only got one morphism, but then it's got like a bunch of two morphisms. It's a k-pi2 space. So then there's one two morphism for every element of the fundamental group of G, because it's K2Z. And so then now, like if you think about like what, like now if you think about like what would be a functor from that category into the two category of categories, you would just replace this object by a category. This thing would have to go to the identity functor, and then you would just get a bunch of morphisms with the identity functor. And that's what this thing is. Okay, so that's like what he says like on one side. And then on the B side, he says sort of the same thing. His ansatz is just that if you have the B-type 2 category associated to a cotangent bundle, you should just take C. If I want to do T star G Langlands dual, I should just look at coherent sheaves that are linear over functions on G Langlands dual, which is also equal to categories that have an action of this particular monoidal category. And similarly on this other side. And I guess what I wanted to say is that they match. I guess this isn't seeming very productive, but the point of all of this stuff is that if you want to make Telemann's thing work out, the thing that you learn is if you study T star C star and you study the A model, is that you want it to be generated by this cotangent fiber, and you want its endomorphisms to be computed by wrapping. And you want this thing to be generated by the thing that's transverse to the skeleton, being the cotangent fiber. Because this would give you that the endomorphisms of this guy are going to be just the category with an integer's worth of objects and then basically with monoidal structure given by plus. And then if you look at like modules for that, that exactly recovers Telemann's definition of being a category together with like an integer's worth of automorphisms. So that's how I knew in this example that I wanted to choose things that were generated transverse the skeleton. This is like not a mathematical argument. It's just I'm trying to like make everything consistent. All right, so I think that I should probably stop, but let me just say the final thing about this is that the thing that you can, that basically when you consider all of these things, this object here, which is generated by components of the skeleton, this thing, if you were to decategorify and just look at the category of sheaves generated by this, you would find that this is like basically the simple object. And this thing turns into the projective object. And so when you finally put like all this stuff together, you find that what you expect to have happen with this two categorical 3D mirror symmetry is that when you decategorify it, you should get you find that you should basically get what's called category O, but I haven't really defined that for you, so I'll just call it the category of microsheaves. Generated by the projective object. And here, you get the category of microsheaves generated by the simple object. Okay, and this is like going to be completely irrelevant. So the conjecture that you end up finding is that you expect that this two categorical 3D mirror symmetry should decategorify into something which is called symplectic duality, which is an equivalence between these two categories of microsheaves that swaps the projective and the simples. So maybe I feel like I've like really not done a good job, but maybe I should stop.
Okay, well, I guess we can ask a few questions in a moment, but let's thank Justin.
Thank you.
And yeah, he had a tough job talking to physicists, so.
No, I mean, that wasn't it.
No.
It was just that I realized that I had packed way too much in,
So yeah, it happens. So here, when you say symplectic duality, this should symplectic duality. You say that this is the statement between A3D of like, let's say M lambda and B3D of M.
No, so symplectic duality is actually like so this thing is like a decategorification statement. So I'm saying you should take this 3D thing,
yeah,
and reduce it to 2D. The reduction that I'm doing is in an omega background. Okay. So I'm doing like a reduction to 2D and omega background. And like what you end up getting is like on the B side, you get like a 2D B model, like deformed by like a Poisson bivector. And on the A side, you basically get like a 2DA model deformed by a B field, being like the imaginary part of the complex symplectic form. And you end up getting like an equivalence of those things. And so that's like a statement that like Braden, Proudfoot, and Licata and Webster called symplectic duality. So these two categories. So yeah, so if I had been like a little bit more careful, this thing actually would have been DQ modules.
What I know as symplectic duality is that you have some geometric space with a symmetry and another geometric space with some symmetry and deformations of one or the symmetries of the other. And so it's kind of
so that was basically just this
Higgs-Coulomb duality.
Yeah, so that was just strictly this matching here, right? So this at the level of spaces, that was the mapping that this mass parameter, which determined the GIT, which determined the resolution, like matched the mass parameter, which determined this Lagrangian skeleton. Sure. So that's like that's the statement at the level of spaces.
Yeah.
But then like the statement that Braden, Licata, and Proudfoot and Webster gave was not a statement strictly about spaces. They gave a statement about categories.
Mm-hmm.
And like basically, and their statement about categories was that you could look at the Fukaya-Seidel category of one of these spaces with one of the skeleta and like this B field turned on. And, or DQ modules of the mirror space with the skeleton, which is basically the B model deformed by a Poisson bivector, and those things would be the same. Although the way that they actually gave it is they just said DQ modules on both sides because there's like an extra equivalence that tells you that the Fukaya-Seidel category was the D modules. So there's no, so you could just say DQ modules, DQ modules. So the statement that they said is like you look at like one of these 3D theories, you turn on this mass and Fi parameter, so you resolve, you have this skeleton, and then you do this like reduction and look at this particular like deformed A model and deformed B model, and they're the same in their mirror.
In the symplectic duality, what is the pair that is dual to each other? So it's A3D on one side and B3D on the other, or would it be A3D of two different things?
Sorry, did you say in the symplectic duality or?
Yeah, so because here you say you wrote symplectic duality at the bottom, but it's under an isomorphism. And so I'm still kind of confused just about what you call symplectic duality, because
so for me, symplectic duality is the decategorification of 3D mirror symmetry, of two categorical 3D mirror symmetry. So two categorical 3D mirror symmetry is a statement about that this Fuder two category.
Yeah.
And then because things are non-compact, you need to incorporate the skeleton in some way.
Mm-hmm.
And so the way that I was incorporating the skeleton was by choosing the set of generators being like these by doing wrapping and choosing these generators transverse to the skeleton. And then on the B side, you have this KRS category, also with the mirror geometry, and those things are the same. And then this decategorifies to a statement that people called symplectic duality.
Mm-hmm.
So symplectic duality is, for me, it's explicitly this isomorphism.
Yeah, so you are using mirror symmetry. Now, since this work of Braden and the others, there's been a different formulation of symplectic duality that Julius was referring to, that you fix a quiver and you say that the Coulomb branch of this quiver is symplectic dual to the Higgs branch of the same quiver.
Yes.
Now, the formulations you've done today was only Higgs branch, only hyper-Kähler.
Well, I used Higgs branch of the mirror, but that's the Coulomb branch of the original theory.
Yeah.
So there is a Coulomb branch over here.
Mm-hmm. So that, I think that's the question that Julius was referring to. That how could you formulate this without referring to 3D mirror symmetry? right? Well, if I allow for Higgs branch and Coulomb branch, then I don't need to use 3D mirror symmetry.
That's correct. So you could say, that this is something. So okay, so here's the part where I erase something that now. Yeah. So you could say that this thing is like MH with like the Lagrangian corresponding to like your mass parameter. And you could look at the A3D is B3D of the Coulomb branch with the mass parameter determined by the Fi. Sorry, here you resolve using the Fi. And then you use your Lagrangian using the mass. And then you could say that this is the Coulomb branch resolved using the mass and with this Lagrangian incorporated with the T. And this would be the same.
Yeah, and he was also referring to symmetry versus resolution deformations.
But I think that's in the lambdas.
So lambda refers to some symmetry operation.
So lambda is the mass, is like the real mass parameter.
But is it also a parameter associated with the symmetry of one of those spaces?
Yes, M is the symmetry of this space.
Mm-hmm.
And then T gives you a symmetry of this space.
Mm-hmm. Yeah.
Okay.
Yes. So, yeah. So maybe I should have. That's right. But let me just say that the thing that I learned from doing this in the only example where we can compute is that this statement is actually too naive.
Uh-huh.
And the reason is that this A model can detect the GIT quotient. Like if you're if you think about like the 3D A model for like, just like U1 with a hyper, say, and you ask like, what's like the Hilbert space on like a Riemann surface? It's the cohomology of the space of vortices, right? So like it's symmetric powers of the curve, or some homology of the sum of the symmetric powers of the curve, and that like it can see like more than just the GIT quotient, like the Higgs branch, which would just be a point, like in the space. And these two categories, you can recover the Hilbert space. And so like basically like the reason that I phrase this in terms of 3D mirror symmetry instead of Higgs Coulomb duality is that this A side is sensitive to the gauge theory nature. Because like, if you like the example that I like to think about is if you think of like all of the H to the N's with U1 to the N acting on them, like all of these things, your Higgs branch is just a point generically. But the mirror to these things is Hn. And so like if you tried to claim that like A3D of a point is dual to like A, and here like your skeleton is also just a point, is dual to like B3D of Hn for all n, like this doesn't make any sense. So this is like your MC, right?
Yeah, sure.
Right. So this side depends on n and that side doesn't. And so the way that like the way that this is solved in which I didn't really get to talk about at all, but the way that this is like in the example that we have actually worked out, this A3D is sensitive to the quotient presentation. And the reason that that's not surprising is that, it's just that like the Hilbert space is also sensitive to the quotient presentation. So like, and the two category knows the Hilbert space. So you shouldn't be surprised. Like in particular, like it knows all the 3D Seiberg-Witten invariants, right? Like H mod U1 like knows all the 3D Seiberg-Witten invariants. So like it better not just be a point. So that's why I don't phrase it this way.
Yeah. Very good. Do we have more questions for Justin? Okay, because then I think we should thank him again.
Yeah, anyway.
And
I'm sorry.
we can go off the record and we can still